Line integrals part 3. Before we talk about this other application or interpretation of the line integral, let's remind ourselves of a few things. And a side note, sometimes I do examples in 2 dimensions. The idea is easily extendable to 3 or vice versa. So consider a curve in space, or in this case a curve in the plane, r equals x of ti plus y of tj. And I want to consider the displacement vector, delta r, equals r1 minus r0. And my claim is that this is approximately t times delta s, where t is the unit vector r prime of t over the magnitude of r prime of t. So I have a picture showing it. The red vector is t, a unit vector in the direction of r prime. And so if I did delta s times t, that would be approximately my displacement vector r1 minus r0. Now it might not look like that, but imagine if we shrunk delta r down so it's incredibly small. If we were to do this, we would shrink r1 back towards r0, then we would see that t times delta s does indeed get very close to the displacement vector r1 minus r0. Now I want to show you the algebra of this as well to remind you of a few things. So s, recall, is the integral of the square root of x prime squared plus y prime squared dt. So ds dt equals the square root of x prime squared plus y prime squared. All right, so ds dt equals this, and then I'm just going to multiply the dt over on the other side. But recall that ds therefore is equal to the magnitude of r prime of t dt. So algebraically, I want to show you the same thing that this equation holds. In fact, it's equal when we shrink the displacement down to 0. And I want to show you this algebraically because t times ds equals r prime of t over the magnitude of r prime of t times ds, which is the magnitude of r prime times dt. So t dot ds is r prime times dt. And since dr dt is just another way of writing r prime of t, we see that t dot ds is indeed the displacement dr. So let's consider the idea of work. Suppose that we have a force field equals pi plus qj plus rk, where p, q, and r are functions of x, y, and perhaps z in this case. And F is a continuous force field in 3 dimensions. The work done by a constant force over a distance is given by the formula F dot d, where d is our displacement vector. But we just talked above about how our displacement vector is what? Well, it's dr. So one tiny bit of work over a small displacement vector will be given by f dot dr. And if we want to find the total work over a curve, then we would need to sum all of these individual components together. So another interpretation of the line integral is something that gives us work done by a force field over displacement. That is the integral over a curve of f dot dr. Now, let's look at an example. Let's find the work done, and we'll do this in the plane to start, of our force field F equals x squared I minus xyj. And we want to move an object over the quarter circle parameterized by r equals cosine t I plus sine tj, where t is between 0 and pi over 2. So our work is going to be the integral of f dot dr. We already have r of t, that is given. So we need to find r prime of t. Right, which is dr over dt. Or dr is r prime times dt. And we'll make that substitution in just a bit. But this is why we need to find r prime. So r prime is going to equal negative sine ti plus cosine tj. This is our r prime vector. Now our f vector, parameterized, is going to be x squared. Well, this is x of t, right? So cosine squared t I minus x cosine t times y, and of course this is our y of t right there, times sine of t, j. And then if we integrate over our curve, so from t equals 0 to pi over 2, because we have parameterized it, we want to do f dot dr. So it's going to be the dot product of f with r, which would be cosine squared times negative sine, so negative cosine squared t sine t, and then negative cosine t sine t times cosine t, so another negative cosine squared t times sine t, and then dt. So now we just have to do the algebra on this one. We get the integral from 0 to pi over 2 of negative 2 cosine squared t sine t dt, where u is cosine t, and then du is negative sine t. So if we integrate this one, we're going to end up with 2 times cosine cubed t over 3 from 0 to pi over 2 equals 2 times, actually let's do 2/3 times, cosine of pi over 2, which is 0 cubed, minus cosine of 0 cubed, 1. And that is the work done by this force field over that curve. And let's do one more example, but let's do this one in 3 dimensions. So let's evaluate the line integral of f dot dr. where our force, which will be a function of x, y, and z, will equal xyi plus yzj plus xzk. And c, let's just parameterize this one. I'll parameterize this one for you. We'll say x equals t, y equals t squared, and z equals t cubed for t between 0 and 1. All right, well, let's parameterize everything. We will write f as x times y, so t cubed I, plus y times z, so t to the 5th j, plus x times z, so t to the 4th k. And then r prime of t will be x prime I plus y prime j plus z prime k. And then our inner rule will be from 0 to 1 of f dot r prime, or f dot dr. So we'll have t cubed plus 2t to the 6th plus 3t to the 6th dt, which is going to equal t to the 4th over 4 plus, and notice here we have 5t to the 6th. So when we integrate, we will get 5 over 7t to the 7 from 0 to 1. Plug in the top limit, we get a 4th plus 5/7 minus, plug in the bottom limit, we get 0. And if we put this together, we get 27 over 28.